So before I get into our last bit of chapter 7 tonight, I want to talk a little bit about what the test is going to look like on Tuesday, really what all of our tests are going to look like. I am going to post the test in chat on Zoom or on Canvas, whichever one works more easily, right at test time. So don't worry about printing it out. Basically, I am not going to write it in a way that I'm not intending for you to write your work on the document that I send out. So have your own notebook paper ready, lined, plain white paper, whatever you like. But yeah, basically, yeah, don't take the time to print out my document. You're just gonna write all your work out on whatever paper you have, and then like most of you have been doing with the quizzes, just take either a photo or a scan and post it on Canvas, and that'll be it. A few of you, it looks like on the quizzes, are using a writing tablet, which you will not be able to do for the test. Any questions on any of that? One thing I said on day one, but haven't really brought it up since. I think everyone here has the capabilities of webcam and microphone. If you don't, please let me know. But I'm going to insist on your camera and your microphone being on while that test is happening. So yeah, if that's something you don't have available to you, please let me know as soon as you can, and I'll see what we can do for you. All right, if there are no questions on any of that, I will, actually, there's one more thing I need to let you know. If you go to Canvas and go to modules, I just added a new module at the bottom. It says Exam 1 Prep or Exam 1 Prep Resources, things like that. Right now, the only thing in there is basically a PowerPoint presentation that has kind of a one sample problem from every section we've done so far. In a couple of days, I will add solutions there that I really recommend you not look at before you've tried things on your own. I will also, hopefully by the end of tonight, I'll be adding some sample problems from the online text that you can use to practice with. But you know, a lot of good things to review. So homeworks, quizzes, all the supplemental stuff I put on there. None of that's going to be due, but it's just extra practice for to help you get ready for Tuesday. And if you need anything else, yeah, as always, please let me know. So let's get going. So the first section I want to do today is, and this is a very short one from the book. Basically, you know, I've given you a few different integration strategies so far. I am not necessarily going to, on the test, ask you to use any given one of them for a certain situation. It's going to be up to you to figure out, you know, what's the best approach to take. So we're not going to necessarily work through the integrals I'm about to show you, but I do want to talk about what the best approach is to use and why. So this first one, based on the approaches that we've done recently, what's the right way to attack this one?
Convert tan x into sine cube x by cos cube.
Sorry, convert it to, here's what I think I heard, which I, okay. So yeah, that might be helpful, but so that's sine cubed x over cosine to the sixth x dx. But what kind of approach are you using here, even in doing that?
Or we could do the 1 by cos cube x, like make it into sec cube x, like, and that's just straightforward.
I don't think what you just described there is true. But I'll go ahead, Rias.
No, would that work? Like, because it seems like it seems to work. Like, I don't know.
You kind of cut out a little bit, but here's what I think I heard. Is that you were relying on this right here.
No. I was trying to think about, like, the 1 by cos cube x? That could just also be rewritten as like c cube x.
Okay. That's true. So integral of tangent cubed x, secant cubed x. So, like I said, I didn't necessarily want to finish this integral. I believe we could, but what I really wanted to focus on is, what the right approach is. And in all the things that Rias has suggested, he's kind of basically everything he's suggested so far kind of is from the same arena, the same strategies. So what we're really looking here is, we're doing trigonometric identities. Yeah, I believe that converting cosine cubed into secant cubed is a good idea. And then maybe it's worthwhile to take one more step. Where would I go from here?
We could separate sec x tan x.
Okay, we want to factor out a secant x tangent x. That leaves us with tangent squared x, secant squared x, dx. So why are we pulling out a secant x tangent x?
Yeah, because even you rewrite tan square x as 1 minus sec square x, and then when you split the integral, I'm sorry, it would be like when you consider u equals sec x,
right?
The derivative of sec x is sec x tan x, and it.
So really, everything you're doing here is based on this derivative, secant x. Derivative of secant x is secant x tangent x. So, yeah, if you're marching towards u substitution, you've already had your du, which means you need your u to be secant, and it can be secant to some power. But yeah, using the right Pythagorean identity to transform or to replace this tangent squared x with something involving secant squared, that's the right way to go. But yeah, one thing I'll point out here, if you see trig functions, especially raised to a power, that's usually a pretty good indicator that you're going to use trig identities to make some kind of modification so you can make the integral possible. Any questions on any of the identifications that were done here? All right, let's go again. What method would be most useful for this thing?
would be U substitution.
Yeah, I think U substitution would be the best. So what's a good candidate for U in this case?
The square root of x.
Square root of x.
Would that work?
That's what I would like to see here. So if we have U equals radical x, then what's du equal to? I guess we should start with du dx first.
One over 2 to the square root of x.
Yep, 1 over 2 square root of x. Well, what does this mean for dx? Actually, let's go ahead and cross multiply. Two radical x du equals dx. Is that okay? So if I drop this in, I'm going to have e to the u times 2 radical x du.
I think, yeah, it would work because you would have that you
So right now the substitution is not done because I still have this x term in here, right? Am I stuck with that x term in there, or can I do something about it?
Can you make it u?
Yeah, that is what u equals. So I can absolutely just transform this one more time to 2u e to the u du. So yeah, certainly substitution got us to a place where we can do something, substitution. And what was it about this situation that told us substitution would work?
It was like a function inside of a function.
Yeah, so anytime you see a kind of a natural composite of functions, that's usually a good clue that you're going to use integration or substitution, integration by u substitution. So now we have this integral of 2u e to the u. Is this something we can handle directly, or do we need to use some other tool?
Another substitution? Can you do that? What would you... Professor, what is the derivative of e raised to x?
The derivative of u raised to x?
No, e raised to x.
Oh, that's a good question. What is the derivative of e raised to the x?
X times e raised to x. Is it
just e to the x?
E raised to x. Oh my god.
Yep. Right. Yeah, this is that a special function whose derivative is it's always equal to its own derivative. And because of that, it might not be worthwhile to try to use this with a substitution because it not really going to make much change. So I don't know if another substitution is going to get us beyond this, but what other process can we use? I think, just by looking at this, I can see that, I don't really have a good integral for, even if I pull out a constant, I don't know what the integral of u e to the u is. But there is something we've done that can help.
Integration by parts.
Yeah, integration by parts is a good candidate here. I'm going to go ahead and rename this. I'll call it t e to the t dt. Because we so often use u and v, So from here, how would we break this down? What would become u? What would become, or yeah, someone give me a hint on how to break this up.
Okay, take t equals u and b equals e.
So if u equals t, then dv becomes the rest of it. And I think that's a good move. I know that when differentiating t will make it simpler, it'll become 1. Integrating e to the t won't make it any more complicated. It's one of the nice things about e to the x is that if it is its own derivative, then it's, you know, up to that constant, it's equal to its own integral as well. So yeah, from here you could absolutely set up integration by parts. So sometimes you'll have to use multiple techniques to handle a certain question. All right, how about this thing here?
Division and then a partial fraction.
Yeah. So what's the clue here that partial fractions is the approach to use?
It's two polynomials being divided.
Yeah. So you're looking at, remember, term we use is rational function, which by definition is a polynomial divided by another polynomial. And I also heard Arias say that our first step in this process would be to do long division, which I agree with that. While we're here, and since this is an important piece here, let's go ahead and factor this denominator. So someone tell me how this denominator factors.
You can factor out an x.
Okay, let's start by factoring out an x. That leaves us x squared minus 3x minus 10. Does this quadratic factor any further?
X plus 2, x minus 5. X plus 2, x minus 5.
X minus 5, x plus 2. And now we have 3 linear factors. So we got 3 linear factors, all distinct. So what is the partial fraction decomposition going to look like here?
X raised to 5 plus 1 by... No, x raised to 5 by this term plus 1 by that.
Sorry, hold on one second. All right, so remember the partial fraction decomposition, kind of the basic fractions we use don't really have much to do with the numerator. They really all come from what the denominator looks like. So if we have these 3 factors here, all linear, degree 1, x minus 5, x plus 2, what does that mean that our decomposition is going to look like?
A over x plus b over x minus 5 plus c over x plus 2.
Yeah, this is kind of the this is the most simple case, I believe, where you have some number of linear factors and none of them are repeated. You just have your simple a plus b plus c over each one of those factors. Any questions there? All right. I'm hoping these ones are kind of easy to identify. I mean, rational functions are, especially if they're more complex. I mean, technically, this is a rational function, but there's not really any decomposition you can do to it. But if they look more complex like this, if they can actually be factored and divided, then you pretty much know you're going to go to some partial fraction process. All right. How about this one?
You can take substitution, right?
Okay, let's try it. So if we do substitution, then that means we need a u. So what should we try?
Natural log x.
Natural log of x. Doing that would force du to be 1 over x dx. What do we think? Will that substitution help us with this integral?
Yeah, I think so.
Yeah, so this integral just becomes du over u to the half. Or u to the negative half du. And this one, I mean, it looks kind of, it might look kind of daunting when you first look at it, but if you get the right substitution, it's really not so bad. Ends up coming out to be 2 square root of u plus c, or 2 natural log of x plus c. All right, and I think I have one more. Yep, this one here. How would we handle this one?
Would you do integration by parts?
Let's try it. So integration by parts. What would our u be equal to? And what would our dv be equal to?
Would u be x cubed and then dv be sine x?
Let's try that. So if we do u equals x cubed, du is 3x squared dx. V would be negative cosine x. All right, so if I apply integration by parts, this is going to be uv, so x cubed, sorry, negative x cubed cosine x, minus the integral of v du, so that's plus 3x squared cosine x dx. So does it seem like integration by parts was the right way to go?
I don't know, because that x squared, like, yeah.
So it's x, this is x squared now, right?
Yeah,
But we started off with x cubed, right?
Yeah, but like, how do we go after that? Like, what is the next step?
Let's do this. Let's break it down into y and dz. And let's stay with what Colin gave us. Put the polynomial part as y and the trigonometric part as dz. That'll make dy equal 6x dx. And z will be equal to sine of x. So then this one will become yz, so 3x squared sine x, minus the integral of z dy, 6x sine of x. So that's as far as I want to go with this, but hopefully you're seeing the integration by parts is getting us closer to being done. Sometimes you'll have to run through it multiple times. I'll tell you right now that doing it one more time will get you to a place where you can finish it. If you're not convinced, I encourage you to give this one a shot after I post these slides. But yeah, doing integration by parts a third time will finish this. But remember, integration by parts, just because it's the right way or it's because it's an acceptable way doesn't mean you're going to be able to get by with it just once. Sometimes it takes a couple of iterations. Any questions on this?
So there's just no other way.
If there is, I don't see it off the top of my head. I am almost certain that so let's think about the other things we have available to us. I'm almost certain that integration by substitution would not work. Let's just think about the kind of things that substitution is good for. Substitution is really good for if you have like a natural composite function. Which for here, I really don't see. Certainly not a rational function because it has trigonometry in it. It's not just polynomials. What else have we done? And we've done trigonometric, trig identities, but sine of x can't really break down any further. I mean, so let's talk about, ruling things out is nice, but maybe we can be a little more convincing about why integration by parts is the right way to go. So think back at when I taught you how to use integration by parts. Do you remember what rule of differentiation I kind of showed you that this was coming from? What derivative rule was that? I'm sorry, what was that?
The product rule?
Yeah, it was a product rule, right? So, and product rule is when you have two different functions multiplied by each other, which this situation most closely resembles. I have the function x cubed multiplied by the function sine of x. So that fact that you can kind of break this thing into two smaller functions that are multiplied by each other, that's usually a good hint that you want to go integration by parts. Really, integration by parts, it really is the product rule of integration. Any other questions about this stuff before I move on? All right, that is all for 7.5. Post that in a little while. So moving on to 7.7. So sometimes we're going to be dealing with integrals or functions that just cannot be integrated. And really, that's a lot of functions. When you were in Calc 1 learning how to take derivatives, the vast majority of functions that you run into are going to have derivatives that you can find. But that doesn't always mean that you can find their integrals. So if I ask for the integral of a function and I can't really find its antiderivative, it would be nice to have some way to approximate what that integral is. So I'll give you a few methods. We're going to go do a few examples of them. But first, I just want to illustrate them for you. So I have a curve here. And I don't remember what the definition of this function is, but I do remember that it cannot be, I can't find the antiderivative for it. So let's say, for example, I think the quintessential application of integrals is to find the area under a curve. If I want to find the area under this curve, I can't just take a definite integral the way that you're used to. We'll have to do something a little different. And remember that, the way you probably saw this in Calc 1 is, if I want to find this area, then really what I'm doing is I'm breaking up this region into all these little rectangular strips. And then I'm going to find those areas and add them all together. And then the smaller I make these rectangles, the better estimate I'm going to get for the area. And essentially what an integral is when I make those rectangles really, really small. But these ones, I can't do that because I can't find the antiderivative. So what do I do in those cases? So our first method we're going to look at is the left endpoint approach. So I have 5 blue rectangles here. And basically what I'm doing is, I split my my interval, which was 0, 1, and I split that up into 5 equally wide intervals. And all of the height of all these rectangles is just the left-hand side of the function over that subinterval. So I think the easiest way to look at this is to think about it in terms of an area. So let's just kind of go through this. How would I find the area of this first rectangle here?
Just the length times width.
So the area is going to be length times width. But can we be a little more specific about that in terms of the function? In fact, let's make it a little more applicable. Let's call it base times height. How long is the base of this rectangle?
.2.
0.2. And what's the height? Let's say this function is called f. This function is called f. So then what's the height of this rectangle?
0.1.
What's that?
0.1.
It might not be exactly 0.1, but can I use the function f to give me like an exact?
Oh, I guess it'd be f of 0.2.
It's actually not going to be f of 0.2 because look out here. We're actually using the left-hand side of this of the rectangle, right?
Oh, f of 0.
That's f of 0. So we're going to have more area. That's the first area. How do I find the area of the next rectangle?
Be 0.2 times f of 0.2.
Yep. And hopefully you're seeing a pattern here. So they're all the same width, or all the same base length, but I'm just taking the left end essentially what I'm doing here is I'm just finding the area of a bunch of rectangles and adding them up, just like, you know, the simplified version of what an integral always does. Any questions on this first one? All right, so next one's quite similar. This next one's the right end approach. And same curve, but now the heights of these blue rectangles are different. So let's reflect that difference mathematically. How would I find the area of these rectangles?
.2 times f of 0.2.
So this time, instead of starting with 0 or f of 0, I'm starting with f of 0.2. But again, it's a very similar approach. In fact, I'm just going to go ahead and factor out the 0.2 and add up all the heights to start with. All right, so left and right end approach are very similar, and the last, or the third one we look at is the midpoint approach. And really, yeah, we're looking at rectangles again. And only thing that really changes is where I'm sampling this function. So I don't have any idea what the antiderivative of this function is, but I can evaluate the function if I know what it is. So if I'm using this midpoint approach, what's my first function value going to come from? What x value?
.1.
Yeah, 0.1. And then it's just going to be still evenly spaced by 0.2. All right, and then the last method we're going to look at here is different from the rest. This is the trapezoid approach. So instead of dealing with rectangles and finding their areas, I'm going to have to find the area of a bunch of different trapezoids. Does anyone remember how to find the area of a trapezoid? All right, if you don't, then let's try to build up to it. So maybe we don't know how to find the area of a trapezoid, but we do know how to find the area of a rectangle. So let's take this first region here. And I'm going to replace this trapezoid, or at least the top of this trapezoid, with a straight line. And because the upper boundary of this trapezoid is a straight line, then I can pretty easily figure out where that average value is. Don't even really need an integral to find the average value of that top side of that trapezoid. So now I'm basically taking the area of a rectangle. But how did I find the area of that rectangle? Certainly it's going to have to do with the base. So I'm multiplying the base times, how did I find this new height, this horizontal red line? How did I find that height? Or let's put some numbers to it. Maybe that'll be easier to think about. If this y value is 0.1, and this y value is 0.6, then what is the y value of this red line?
Like right in the middle is like 0.35.
Yeah. So, and you said it right in the middle. How do I find the number that's right in the middle of two other numbers? How do I do that mathematically? So let's call that height 1 and plus height 2. And really, I'm just averaging two numbers. That's how I found that this middle height here. So this right here, this is how you find the area of a trapezoid. So my base is not going to change, but it's the height that I have to factor or deal with to find that that average between them. So essentially, the area of a trapezoid is the base times the average of the heights. So let's apply that to these trapezoids here. This area is going to be, and the base is always going to be 0.2. And the height we're going to deal with is going to be f of 0 plus f of 0.2 over 2. And I'll do one more, then we'll just omit the rest. Plus 0.2 times f of 0.2 plus f of 0.4 divided by 2. And then concluding with the last one, which is going to be 0.2 times f of 0.8 plus f of 1 over 2. So I'll go ahead and stop here. Any questions about how this one works? It got really quiet on me when I started this one. So hopefully it becomes more clear when we actually do an example or two, but let's talk about it if you need to. Any questions about this? Okay, so let's go ahead and do some examples. So I want to use the midpoint approach and 5 intervals to approximate 1 over x, this integral of 1 over x. So our interval is 1 over 2. So the first thing I should do is to figure out what my subintervals are going to be. I'm going to have 5 subintervals, and I want them all to be equally spaced. So that means the first one's going to start at 1, and where will it end?
One point two.
1.2. So we have a width of 0.2. And really, if you want to look at it this way, our delta x is just going to come from, first of all, how big is what's the measure of our interval? How wide is it? And I want to divide that width by 5. So that comes out to 1/5 or 0.2. And the rest of these are going to follow suit. So here are my 5 subintervals. All right. So let me draw a little bit of a graph here for our first one. I know it looks something like this. And I'm going to be finding a few different values. So we're going to do the midpoint approach. So I'll let you all tell me what values we're finding. Basically, what we're going to do is this. We're going to find value or pick values of x and find values of 1 over x. So if we're using the midpoint approach, what 5 values of x do we need to be choosing? Or I guess just give me the first one.
1.1.
1.1. So the first interval goes from 1 to 1.2. So I want to grab the point right in the middle. That'll be 1.1. Similarly, I want 1.3, 1.5, 1.7, 1.9. So now that we have those 5 values, now we can find our 5 values of the function. And let's do 5 decimal places. So what's the corresponding value with the first one there? Okay, so we got our 5 values. Now, how am I going to use those to find my, or to approximate the value of this integral?
Would it be 0.2 times all of those values added together?
Yep. So really, yeah, to find, I know that all these rectangles that I'm going to build are going to have the same base. So really, I can just multiply all the heights or add all the heights together and then multiply them by that 0.2. So 0.2 times 0.90909. And while I'm writing this out, if somebody could get me a final answer here, that'd be fantastic. Somebody have it for me?
Mm, 0.69191.
0.69191. That sounds reasonable because do we have a way to integrate 1 over x dx?
No way.
We actually do. We can integrate this one.
Uh,
This comes out to be the natural log of x. So natural log of 2 minus natural log of 1. Natural log of 1 is 0. So we get natural log of 2, which if you plug into your calculator is about 0.693. So our estimate ends up being pretty good.
I mean, I still, when I try to think about it intuitively, like, I still don't understand how it's like log x. But then you try to do it the normal way, it's just.
Yeah, if you try to do it the power row way, it falls apart. That is not a question I can answer quickly. Let me either find something or put something together. I'll put it on the Slack.
Sure.
But yeah, it's not a question I can answer fast.
Sure.
It's a good one though. All right. Any more questions about this first example? Okay. All right. Same function, different approach. So we want to use the trapezoid approach in the 5 intervals to approximate this region. We're using 5 intervals again. So that means I still get to use the ones I had before. What am I doing? All right. So there's those 5 intervals. Let me draw a graph in again. So x equals 1, x equals 2, 0.2, 0.4, 6, 8. So the first thing we need to figure out, since we're using the trapezoid approach, let's make a table again. What's the first value of x we need to look for? What's the first value of x we need to look at this time? So maybe I should draw a trapezoid in here. So there's my first trapezoid. What xy pairs or what f of x pairs do I need to accurately draw this trapezoid?
I'm confused if it's like I know it's the like height 1 plus height 2 divided by 2, but is it like f of 1 plus f of 1.2 divided by 2, or is it?
Yeah. In this case, yes, it will be. But we're not quite there yet. Really, I'm just trying to get all my x and y pairs. But you essentially answered it for me. I know I need the y values when x is equal to 1, x equals to 1.2. So, among others, but really, to do the trapezoid approach, I need basically all the endpoints of all the intervals. So I need 1, 1.2, 1.4, 1.6, 1.8, and 2. So first and last are pretty easy. This is going to be 1. This is going to be 0.5. And then need a calculator to get the rest. Again, I want to go to 5 decimal places if I need them. All right, so, and this one, I mean, rectangles are about as simple as they get. Trapezoids are maybe something you haven't taken the area of in a while. So let's just do this one as slowly as we need to. So area 1. How do I find the area of that first trapezoid?
.2 times the 1.8333 divided by 2.
So yeah, the sum of those first 2 endpoints. So that's area 1. And just so you can see what the changes are, tell me how to finish area 2 here. How would I make that calculation?
.8333 plus 0.7129 divided by 2.
So really, the area 1 and area 2 and so on. Let's go back and label these intervals. 1, 2, 3, 4, 5. Basically, how I get those areas, I'm going to get the heights from the 2 endpoints of those intervals. So plus 0.71429 all over 2 again. So it is going to take me a bit of time to write out all 5 of these, but I think it's worthwhile so they're on Canvas. So if someone wants to start working on a final answer for me, that would be fantastic again. And because of the last example, we sort of know what we should be close to. Did anybody have anything yet?
I got 0.695636.
0.695636. Thank you. And we know that, I mean, that's still very, very close to what we got last time. So I would say that's a very good estimate. Any questions here? All right, so left-handed approach in 4 intervals to approximate this one. So I'll let you drive a little bit. How should I start this one?
Writing out what the intervals are.
Okay, and what are they going to be?
Zero, 0.5, and so on.
Yep, they're going to be the same width. All right, now that I have those intervals, where do I need to go from there?
Could you just go right into like making the equation of just 0.5 times oh yeah, I guess that's we have to find the answer of the function.
Yeah, let's evaluate the function first. So based on our intervals, let's figure out what values of x we need. So I only care about the left end. Maybe a graph will help again. So x equals 0, 0.5, 1, 1.5, 2. So I care about the left end approaches, or the left end approach. So what x values do I need to make this work?
Zero, 0.51, and 1.5.
Yep, just those 4. See, I mean, the left hand, I need the left end of these intervals. So that's going to come directly from just these 4 numbers. When x equals 0, that one's pretty simple. That one's 1. The other ones we're going to need a bit of some calculation for. All right, so we have the function values, all the ones we need. So where should I go from there?
Like 0.5 times the sum of all those values.
Yep. So rectangles are a little easier to deal with. So 0.5 times 1 plus 1 plus 2, 403. And I believe this is what I have, but let me know if anybody disagrees.
Is this integration by parts?
This is not integration by parts. So
No, to retrospect, like the integration by parts.
oh no, in fact, so e to the x squared. This is kind of the quintessential. I mean, one of the classical examples of a function that cannot be integrated. So the antiderivative of e to the x squared does not exist. So if we want to, we can find, or we can approximate a definite integral by doing something like this, but we'll never be able to get it exactly. So last question I have for you here is, so we have an approximation. Do we think that's an overestimate, an underestimate, or do we think it's pretty good?
I think it's an underestimate.
Okay, why do you think it's an underestimate?
Because the areas, since there's a left endpoint, it's like always gonna have a portion like below the graph.
Right.
There's a point that's not.
So really the area we found is what I'm shading right now. But there's a lot of area under the curve that we didn't get. So follow-up question. Will the left-hand approach always be an underestimate, or is this, is there something else about this that makes it an underestimate?
The function also needs to be positive.
Positive is part of it, but I don't think it's all of it. I think I could draw you a positive function where the left-hand approach would be an overestimate. For example, if I did the left-hand approach here, it would look something like that.
Oh, I guess the slope has to be positive, I guess.
Right. Yeah, the other key here is that this is increasing function. So the fact that I have an increasing function and I'm taking left endpoints, that combination guarantees me an underestimate. So example 4, I don't want to do I don't want to do the whole thing, but I do want to ask you this. What would change? What would be different between the last thing we did and this one?
The points that we found from the function.
Right. So changes from example 3. So points that we sample. So what function values will we need for the right-hand approach here? Made too many of these.
Point 0.5, 1, 1.5, and 2.
Yep. But really, besides that, the process is going to be the same. So like I said, left and right approach and midpoint, they all deal with rectangles. It's really just a matter of where you're getting your values from. All right, example number 5. So I have a graph here that shows traffic on a wireless network in megabits per second on a certain day. So I want to approximate and interpret the area under the curve. So I am not dictating how many intervals we use or what approach we use. So let's do this first. How many intervals should we look at? So we want to do enough that we can be sort of accurate, but we don't want to do so many that it's just, because we're going to be here for the rest of the night.
Good God.
Yeah. I think I'm okay with 4 intervals. So that'll cut us off every 6 hours. So let's look at the graph here. Based on the way the graph looks, is there any approach that might be better than another?
How about the trapezium?
Yeah, we can do trapezoid. Why, or trapezium? Why did you choose that one?
Because a lot of those fragments look like a trapezium.
Yeah, I mean, it already kind of fits that shape, right? So, I mean, if let's say I did left end approach, then my first interval is going to look like that. I mean, I'm already introducing a lot of error if I do something like that. And the next interval, it's going to be even more severe. So I think, I mean, with the kind of behavior you have here, I think, yeah, it makes sense to use trapezoid rule. So let's start by drawing those in. And one thing I want to point out here, I'll go ahead and write trapezoid. One thing I want to point out is, you know, when we were doing work, we had an example where it really became clear how important it is to stay consistent with your units. So On the vertical axis, this is given in megabits per second. Our time axis is given in hours. So we have a problem there. So what we're going to need to do is rewrite, and we'll just stick with the intervals we need, but we need to re-express those in seconds. So instead of 6 hours, I need seconds. So this should be 21,600 seconds. And 43,200 seconds. And 64,800 seconds. And then 86400 seconds. All right, so we're off to a good start, and I think just looking at our trapezoids, how they overlay with the curve, I think this estimate's going to be pretty good using this approach. We don't have a function here that we can kind of plug things into, so we're going to have to read as closely as we can. So let's find these areas. What would the area of the first trapezoid be? Or how would I find it?
Maybe like 21,600.
Yep.
Times the values at, or the average of the values at 0 and 21,600.
Okay. So what do we think those values are?
Like 3 and 2.
I believe 3. I think the second one is probably closer to 1. So 3 megabits per second. I'll say 1.4. So let's go ahead and approximate that. Actually, we're missing something pretty important.
The average of those two.
Yeah, we need to average these. So I will put a factor of 1/2 in front. And we'll figure out how to deal with those units in a little while. All right, how about area 2? Certainly the same base, and we're going to have to average a couple of heights. We already said that, oh, left out the unit. .4 megabits per second. And how about the other one? That'll be, well, 7.5. Area 3, I think they sort of got a gift on that one. Is it okay if we just treat that one like a rectangle? And then for that last value, let's say 2.5. So this total we got 413,640 megabits per second times seconds. So I guess I'll pause for a bit. Does anybody have any disagreements or any questions about how I got that total or any of the subtotals? Okay, so the last thing we need to do is figure out, what does this mean? So I have megabits per second times second. Do those units, when I multiply them together, simplify in any way?
Megabits per second squared.
Let's go ahead and write this out another way. So it's megabits per second, and then that's multiplied by seconds.
Just megabits.
Yeah, it just becomes megabits, right? So but maybe we should unpack that a little more. So let's look at this. Let's go back to the beginning here. The y-axis shows basically the rate of basically data transfer in megabits per second, and the x-axis shows time, which we altered to be in seconds. So basically what this number gives you is the total amount of data that was transferred on this network over that 24-hour period. At 413,640 megabits. Any questions on this one?
Can we just approximate it to be some sort of sine graph or something?
Maybe. If you can find a sine graph that'll closely resemble that, that would be good.
Or it's just it could just be a cos graph, a cosine graph, I guess.
Yeah, I see why you see that. The only thing that makes me a little worried is that a cosine graph is symmetrical. It's what I mean by that is if I were to draw a cosine graph down here, one period looks like that, the average value is going to be 0. So, and I can say that to you now because you know how to calculate the average value of this function. I do not think you can say the average value of this function is 4. And it looks like for the first 6 hours of this graph, the traffic is really low. And then for the next 18 hours, the traffic is pretty high. So that's why I think trying to use a trig graph might be hard to get an approximation of this on. But there are probably, not probably, there are definitely other ways to approximate a curve. I've just showed you a few of them, but there are. I've taken classes where that's basically. I mean, some of you will probably take a class called numerical methods in your math career, depending on what you're majoring in, and really, all those classes are about are finding ways to find better approximations of things using a lot of different approaches. So yeah, there's certainly a lot of ways to do these.
Thank you.
Thank you. Any more questions for the moment? All right, I have 7:39. Let's go ahead and take a break. Let's come back at 7:50. I'll see you then. All right, I hope everyone's back. So our last section we're going to cover is on improper integration. Basically, what happens when you deal with an integral whose function is, either not defined or discontinuous. So let's look at some examples of that. So a couple different ways we're going to look at this is, what if your interval includes infinity somehow? So this first one to look at is, I want to evaluate this integral 1 over x squared dx from 1 to t. And I have a few different values of t I want to look at. So let's just go ahead and get started. So integrating from 1 to t, I'll do a quick rewrite. X to the negative 2 dx. What is that? What's the antiderivative of x to the negative 2?
Negative 1 over x.
Yep, negative 1 over x. And if I evaluate that from 1 to t, I get negative 1 over t minus negative 1 over 1. So 1 minus 1 over t. So really the function I'm looking at, or the integral I'm looking at, if I can draw a quick graph of it. It looks like this. As you approach the y-axis, it's very, very, it goes up arbitrarily high. But then as x gets large, the graph gets, arbitrarily close to the x-axis. So basically, we're trying to find the area in here. So let's say this is x equals 1. And the first one we're looking at is x equals 2. And I think it's pretty clear that from there that, that area is contained. I can find this area. So this integral here we found, we can use this for any value of t, really. So if t equals 2, we'll get that integral is equal to 1/2. So what if instead we have x equals 10? Then hopefully it becomes clear that the area is going to grow because I'm gaining all this this new area here. So if t equals 10, then I have 1 minus a tenth, which is going to be 9 over 10. And I'll put decimals in here too, so it's a little easier to compare. So I got 0.5, 0.9. If I go out to 100, and this is not going to be to scale, but that's okay, I'm obviously going to get a lot more area. So even though the graph is getting, basically my y values are getting very small. They're never going to become 0, but they're going to get smaller and smaller and smaller as x goes on. So I would expect when t equals 100 that this area is even bigger. So 1 minus 100 is 99 over 100, which is 0.99. And you can kind of see a pattern emerging. When t is equal to 1,000, I'll have 0.999. So really, this integral is easy. This is something we've done when you have some finite limit, some finite upper limit like we've had. But what happens, infinity is not our number, so we better use a limit to deal with it. So the limit as t approaches infinity of 1 minus 1 over t. So as t gets really, really large, what's 1 over t going to do? What's going to happen to it?
It's smaller and smaller.
Smaller and smaller? Is there going to be a limit, or is it going to keep getting smaller and smaller?
To 0.
Yeah, it's going to have a limit of 0. So it will get smaller and smaller. It'll never become negative. But really, any positive number I can think of, no matter how small, I can find an x value that'll make it reach that. So because of that, I know the limit is 0, which means this integral is equal to 1. I guess I'll spell it out. So the integral from 1 to infinity of 1 over x squared dx is equal to 1. So this is kind of our first look at improper integrals. Even though our lower limit is some real number and our upper limit is infinity, we might still have an integral that we can find a finite value for. And this is one of those times. Any questions on this first one? All right, let's go ahead and look at another one. All right, so we're going to try the same thing with a similar function. And because we have infinity, I'm going to set up a limit to handle it. So let's deal with this. What is the antiderivative of 1 over x?
Log mod x.
Yeah. Natural log of x. I'm going to leave off the absolute value because we're only looking at positive values. Oh, not that. From 1 to t. And evaluating that, got to keep the limit operator handy. This becomes natural log of t minus natural log of 1. And since the t only has to do with the first term, I'm going to split this up into limit as t approaches infinity of natural log of t minus natural log of 1. But the natural log of 1 just goes to 0. So really what we're left is the limit as t approaches infinity of natural log of t. So as t gets really big, as t goes towards infinity, what's the natural log of t going to do?
Infinity?
Yeah, I mean, it will continue to grow forever. It has no limit. It's never going to stop increasing. So because of that, this limit is infinity. So one thing I meant to point out in this last one, so because this limit exists, this is a convergent, or this integral converges. So, and really all that means is the integral has a finite limit. I just get a number when I evaluate that definite integral. But this one here, this diverges. So when I deal with this limit from this integral of 1 over x, if I have my upper bound be infinity, I will never, I can't get a value. I cannot get a finite value for that. So any questions on those first two? So specifically the difference between convergent and divergent integrals, or why the first one converges and the second one diverges? Anything at all? Right, let's go a little deeper. So let's try to generalize here. So P is some constant, and I want to know what values of P this integral converges for. So let's write down what we know. So what have we tried? We've tried, and this is basically a spectrum of P here. I've tried 1 and I've tried 2. I know at 1, it diverges. At 2, it converges. So can we put a little more, can we make any more conjectures about that? What do you think is going to happen over here for values greater than 2? If 1 over, like for example, if 1 over x squared converges, what do you think 1 over x to the 5th is going to do? Or let's put a couple more in here. Let's say 1/2 and 3/2. Anybody have any guesses for what's going to happen at these points? Okay, so it's okay if you don't. Let's go ahead and try it out. So again, I have an infinite limit, so let's set up a limit operator. So remember that P is a constant. So I can just treat it like a constant, even though I don't have a number for it. What is the antiderivative of 1 over x to the P? Maybe this will help. If I rewrite as x to the negative P dx, what is that antiderivative?
X raised to minus P plus 1.
That's part of it.
Divided by 1 minus P.
Yeah, there you go. Not x. So the antiderivative, like Ria said, is going to be x to the negative P plus 1 over 1 minus P, evaluated from T to 1. So let's work down. So really 1 to any power is going to be 1. So I can simplify this a little bit. So T to the 1 minus P minus 1 over 1 minus p. And, you know, 1 over 1 minus p is just a constant. So if the limit exists, then dividing it by 1 minus p, it'll still exist. Actually, that's not always true. What value of p is going to make this limit not exist? What can you see right away?
When p approaches 1.
Yeah, or no, not when p approaches 1, but when p equals 1. So remember, we're not varying p, we're varying t. So when p equals 1, this limit won't exist. It'll diverge. And that's something we, that just confirms something we just found out. We know that when x equals 1, or sorry, when that power on x is 1, that integral diverged. So we have these kind of 3 test values here. Let's go ahead and work with those. So what happens if p is equal to 1/2? Then that means my limit is going to be, so of 1 over 1 minus 1/2 times the limit as t goes to infinity of t to the 1/2 minus 1. So this right here is really the important piece here. So if t goes to infinity, what is t to the 1/2 going to do?
Also go to infinity?
Yep, it'll also go to infinity. So this right here also diverges. Do you think that'll be true for anything less than 1? And look at this exponent here. If I put in anything less than 1 for p, then that means I'm going to have t to a positive power. And if I have t to a positive power, then as t gets big, that t to that power is not, it's going to keep on growing. The limit's not going to exist. Instead, let's look at what happens if we have p equals 3/2. Then we'll have 1 over 1 minus 3/2 times this limit. 1 minus 3/2 is t to the minus 1/2. And let's go ahead and rewrite that as the limit as t approaches infinity of 1 over square root of t. So you just told me that as t goes to infinity, then t to the 1/2 is going to go to infinity as well. That doesn't change. But now what happens if I have 1 over something that's going to go to infinity? What's its limit going to be?
0.
0. So that limit exists. So I can I'm going to go ahead and fill in this 5 as well. Clearly for anything 3/2 or bigger, that's just going to make that limit, so the limit's still going to be 0, but it's just going to go to 0 even more quickly if I have p being even larger. So now the real mystery lies in this region here. I know I have to be bigger than 1. And I know I can be smaller than 3/2. So let me ask you this. Does it matter how much larger I am or how much larger P is than 1?
No.
No, it doesn't. Because if P is even slightly bigger than 1, then you're going to have, let's just pick something 1.000001. Then that means the limit we're looking at is T to the 1 minus 1.000001, or T to the negative 0.000001. And the fact that that power is negative is all you need. Since it's negative, it will go to 0. So really, all that we need from P here is that it's greater than 1. Not greater than or equal to 1, just strictly greater than 1. Any questions on that or why that is true? All right, let's keep on going. All right, got this integral here. So I'll take my cues from you on this one. How should I start this?
Since it has a limit, do we have to make it a, I'm sorry, since it has infinity, do we have to make it a limit?
Yeah, we do. So let's set up a limit operator. What should I have T approaching?
Negative infinity?
Yep. T approaches negative infinity. And then we'll rewrite this integral from T to 0 of xe to the x dx. Good start. Now what?
Find the antiderivative.
Yeah, let's find the antiderivative. And because of that, let's just treat it as indefinite for now. How do we deal with an integral like this? What technique do we like?
Integration, integration by parts.
Yeah, let's try that. So if we do integration by parts, we need to choose a u and a dv. U being x is probably a good choice since that'll become very simple after I differentiate it. So from here, let's continue with integration by parts. So this becomes uv, so x e to the x minus the integral of v du, which is e to the x dx. That's equal to x e to the x minus e to the x. So now we can continue on with our integral that we're trying to find. So the limit as t goes to negative infinity of x e to the x minus e to the x from 0 to t. So now we can evaluate this integral at both those limits, or yeah, both. So using two limits in two different senses here, but that's okay. So 0 e to the 0 minus e to the 0. So this goes to 0. All right, so now the question becomes, what happens to these last two terms? As t goes towards negative infinity. Any ideas? Here's one thing I'm gonna offer that might make these a little easier to think about. I'm gonna replace this limit with this. The limit as t goes to infinity, positive infinity of this, -1. And basically I'm gonna replace all the t's with negative t's. So I'll make this 1 plus t e to the negative t minus e to the negative t. And what this allows us to do is a rewrite that might make it a little more intuitive. So -1 plus t over e to the t minus 1 over e to the t. So clearly this term right here, this is not going to have anything to do with our limit. If we get basically, if we get a finite number, then subtracting 1 from it's not going to make a difference. Let's look at this third term, the -1 over e to the t. As t gets very big, what's that going to do?
It's gonna like go towards 0.
It's going to go to 0. So basically, if I divide 1 by a positive number that just keeps getting larger, I'm eventually going to go to, my limit's going to be 0. The one that's a little trickier to see is t over e to the t. What's going to happen is t gets very big there. Actually, let me ask it this way. Clearly, the numerator is going to get larger and larger because the numerator is just t. The numerator is going to go towards infinity. For the same reason as before, e to the t is going to go towards infinity. So we have numerator and denominator both going towards infinity. So how do we find the limit for that whole fraction going to infinity? Is there a tool you remember using in Calc 1 that we can make use of now? Does this sound familiar? L'Hopital's rule?
Yes, sir.
Right. So I'm able to use that because the limit as t approaches infinity of t is infinity, and the limit as t approaches infinity of e to the t equals infinity. So I have some indeterminate situation, so I can use L'Hopital's rule. So now here's what I get to use. The limit as t approaches infinity of t over e to the t is equal to the limit as t approaches infinity of the derivative of the numerator divided by the derivative of the denominator. And hopefully we know what this limit is. What's that equal to?
Zero.
That's 0. So we end up getting an integral that converges to -1.
I was kind of wondering for the t over e to the t. I know they both go towards infinity, but I feel like the bottom one goes towards infinity faster.
Yeah, that's
like,
that's exactly what L'Hopital's rule does. So think about what a derivative is. A derivative tells you the rate of change of a function. And you're absolutely right. The rate of change of e to the t is much faster than the rate of change for just t. So that is essentially why that limit goes to 0. Because, yeah, you're right that t and e to the t both go to infinity, but one grows a lot more quickly than the other. Any other questions about this example? Okay. So that's one kind of improper integral. The other one I want to talk about is, oh, never mind. I guess that's coming next. So I have basically both limits involve infinity. I don't really have a way to deal with a limit operator that has more than one limit. So is there a way for me to deal with negative infinity to infinity?
Split it.
Split it into what?
Infinity to some equal interval, like maybe 2 or 0 or something.
0 sounds promising. So from 0 to infinity of, or I'll leave it like that for now. 1 over 1 plus x squared dx plus the other integral from negative infinity to 0. 1 over 1 plus x squared dx. All right, I think that's good. Now, how do I set up the limit operator from there? Or I guess the whole reason I'm splitting this up into 2 pieces is that we can do them one at a time. So limit as t approaches infinity of 0 to t of 1 plus x squared dx. What is the antiderivative of this? hopefully somebody was thinking this, inverse tangent of x from t to 0. Actually, I better write this in a line. All right. What is the inverse tangent of 0?
0.
0. So that one falls off. So now we got to think about the limit of this one.
Pi by 2.
Oh, pi over 2. How do you know that?
Sorry.
No, it's okay. You're totally right. I just want to know how you know it.
Well, tan pi over 2 tends to undefined.
Yeah. So let's think about what tangent. Let's draw a triangle here. And I'll draw kind of a. So I'm looking at inverse tangent. So let's have, call my angle theta here. I want this side to be 1, and I want this side to be, let's call it y. So the tangent of that angle is y over 1, or y. Actually, let's do this. It makes more sense. Let's call these things t. And the inverse tangent of t is equal to theta. So basically, t is going to get very, very, very big. So that means this triangle is going to grow in height while its base stays the same length of 1. So as t gets very big, think about what's going to happen to that angle. That angle is going to get closer and closer and closer to being a right angle, which is why this limit is pi over 2. So I'm not totally sure that everyone's had to think about that before, but so I'll stop there. Any questions on why this limit is pi over 2? Okay, so now we can do the same thing with the negative side of this integral. So the limit from negative t to 0 of 1 over 1 plus x squared dx. We know that that will have the same antiderivative. Okay. So as t gets very large, basically what we're looking at here is the opposite side, or basically t is going to get very, very negative. So what is this limit going to go toward? Think about it this way. If we put this in the fourth quadrant, maybe that'll be easier to think about. So angle theta, call this side 1, and we'll call this other side negative t. So as t gets very big, this triangle is going to get really tall, but it's going to grow tall into the negative y direction. So what angle is that theta going to be approaching?
3 pi over 2.
3 pi over 2, but really the inverse tangent only goes between negative pi over 2 and pi over 2. So yeah, it's an equivalent coterminal angle, but in this case it'll be, I'll break this down into steps, negative pi over 2, which is equal to pi over 2. So this integral from infinity to negative, or negative infinity to infinity, of 1 over 1 plus x squared dx equals pi over 2 plus pi over 2, which is just pi.
I mean, it also makes sense graphically. Like,
yeah, I think so too. It definitely makes sense that it's positive. If you were to just graph 1 over 1 plus x squared, you know, it's that function has a maximum at the y-axis. And then as you go away from the origin, it's definitely going to be decreasing, but it's always going to be positive. So yeah, it makes sense that it has a limit. It makes sense that it's positive. One thing I will leave as an exercise for you all is you can look at this all as one integral if you are careful with the t here. So what if I have t going to infinity and I just make my integral go from negative t to t?
just be 0, right?
No, I mean, this is the same exact integral that we just did.
Yeah, yeah.
So this better come out to pi. But I'll leave this for you all to play with. So before I say that any more about that, splitting this integral up is fine. It's totally acceptable to do that so long as you're thoughtful about what the limits are. I think choosing 0 as that dividing x value was really, really smart. You can choose anything, but let's say we chose 1, then you got to deal with the inverse tangent of 1, which it isn't difficult to find, but now you have to deal with more non-zero values than you might want to. So yeah, if you try to deal with this by only having one integral, and go ahead, Reyes.
Professor, I have a doubt. Like, what if you split it like in like 2 to 8, and
2
then
to 8,
and in negative infinity to 2 and like that? Would we get the same thing?
So here's what I think I'm hearing. So negative infinity to 2, I'll just call it f of x for now. Is this what you're saying?
Yep.
Yeah, so yeah, this will have to work. And that's something I'll let you play with that and convince yourself of it, but yeah, it is totally acceptable to divide up that integral at whatever real number you want. That's totally fine. And yeah, I mean, you know that, you know, for everything I've starred there, you should get a final answer of pi. So I would encourage you to verify that for yourself. If you want to talk more about it later, we definitely can. But I think it's helpful to see that, you know, there is not one way to handle this. There usually are multiple ways to handle lots of these. Any more questions on example 5 here? Okay, now we're going to look at the discontinuous integrands. So this integral, obviously neither one of my limits is infinite, but let's take a look at this function. So 1 over the square root of x minus 2. So 1, 2, 3, 4, 5. If I plug in 2 to this function, what's the value of the function going to be?
Undefined.
It's going to be undefined, right? So my function is going to have some kind of behavior like this. So, you know, with the infinite cases, it's easy to see where you're going to need to set up a limit. With these, it's not as simple. Basically, you got to figure out where the function becomes a problem. And in this case, it's at x equals 2. So let's rewrite this guy as the limit as t approaches not only 2, but 2 from the right. Now let's think about that. Why do I only care about that limit from the right?
I mean, I don't understand. Like 2 minus is like it's not even there in the function.
Yeah, that's exactly it. So this integral has nothing to do with the left-hand side of that line x equals 2. So, and you've seen this in Calc 1, I'm sure, where you may have functions that are defined, whose limits are defined on one side, but not the other. And really, it does not matter to us what's happening with that limit on the left side. So we're only gonna approach 2 from the right. All right, so we have our limit operator set up. What is the antiderivative of this function?
Two times the square root of x minus 2.
Yep. 2 times the square root of x minus 2, and we're going to evaluate that from t to 5, which comes out to be 2 times the square root of 3 minus 2 times the square root of t minus 2. So left-hand term is easy. That one has nothing to do with our limiter of t. What is going to happen as t approaches 2 from the right?
It tends to 0.
Yeah, it goes to 0. In fact, in the antiderivative, 2 is defined. 2 is the antiderivative is well defined at t equals 2. So really, the value of this integral is 2 radical 3, and that is convergent. One other thing I want to point out, so we were only looking at the limit as t approaches 2. Even though we didn't need it, let's think about it. What is the limit as t approaches 2 from the left of, and I'll just look at this, radical t minus 2? Is this also 0?
No, that's a positive. Sorry. It's an imaginary number.
Yeah, this does not exist. because yeah, I mean, if I'm approaching 2 from values that are less than 2, then that square root's never defined. So that limit doesn't exist. So basically another illustration of why the one-sided limit is really what we need to be using. All right, let's look at another one here. So this integral of 0 to pi over 2 of secant x. So do we have a situation where our integral is going to, or where our function is going to be undefined?
At 0.
Let's see.
Oh, no. Cos 0 is 1. Pi by 2.
Yeah, there you go. So remember, secant of x is equal to 1 over cosine x. So it's really, it all depends on what value of x is a cosine at 0. And since cosine pi over 2 is 0, that's where our limiter needs to be set up. So we're gonna have a limit, or how to put the limit operator in. The limit as t approaches pi over 2, but from which side? From the left or from the right?
From the left.
From the left, right? So if we look at our interval here, pi over 2 is the right endpoint. So I really am not interested in anything that happens to the right of pi over 2. So this is our limit here. As t approaches pi over 2 from the negative side, from the left side, this integral. Do we know what the integral, or what the antiderivative of secant x is? I don't think I do. But is there some method that we've learned recently that we can use to help us? Think about what we did last night. We didn't have a good way to take to find the antiderivative of natural log of x. So what technique allowed us to do that?
This one it's kind of easy. You could take it as 1 by cos x and then make it cos square plus sine square x and then just divide it, and then you get the easy answer, right?
So this is 1 over cosine x. And then what did you do from there?
You could just put make one rewrite 1 as sine square x plus cos square x. And then that's just one of them is u and pu and substitution.
Okay, hadn't thought about that, but that'll work. So from there, that should be the integral of cosine x plus sine x tangent of x. So I'm not seeing how to deal with sine tangent.
You don't need to make it sine tangent. You could just keep it as sine squared cos pi cos.
But it's sine squared x.
Over cos.
Yep. Okay. So that'll make this left-hand term sine of x. What happens to this right-hand term?
It won't work.
Yeah, I don't think this is gonna go.
But how about rewriting, because sine square x as something like, can we,
let's try integration by parts, because we know what the derivative of secant is. So let's try this. X secant x minus the integral of v du. And nope, that doesn't get us there either. So let me think about this a little more. So I think in the interest of time, I'm just gonna do this for now. I'll give you this integral, and I'll, in the meantime, I owe you some explanation on why this is true. So this integral is equal to the natural log of secant x plus tangent x plus c. So for now, please just take that on faith, and then I'll give you some detail on that either tonight or tomorrow morning. So if that is the antiderivative, let's keep on going with this integral.
Professor?
Yep.
I mean, is it possible that we can that okay, I'll just afterwards.
Okay. All right, so now we're evaluating this thing. So let's handle the parts of this that we can deal with now. What is the secant of 0?
1.
Yeah, just come out to 1 because cosine of 0 is 1 and 1 over 1 is 1. So this right here is 1. And what's tangent of 0? Hopefully we recognize that as 0. So really the whole the right side of this becomes natural log of 1, which is 0. So now what we're looking at is this natural log of secant of t plus tangent of t. So our best case scenario when evaluating the limit, is secant of t defined at pi over 2?
Are we still subtracting 1 from that or no?
No, so natural log of 1 is 0.
Oh, okay.
So this is all we have left. So we see that secant of pi over 2 is equal to 1 over cosine of pi over 2. But cosine of pi over 2 is 0. So secant of t is not defined at pi over 2, but maybe there's a limit. As angles get closer to pi over 2, then the cosine is going to keep getting closer and closer to 0. So is this 1 over cosine of pi over 2? Is there any finite number that this is ever going to approach? And really, I'm hoping you're seeing that basically as the cosine of t gets very, very small, then the secant of t is going to get very, very large, and really it's not going to have any limit. So because of that, this integral diverges. And really that's independent of whatever happening with tangent. Any questions there?
So since the secant diverges, it just means the whole thing diverges.
Yeah, so really, if the tangent of t diverges for the same reason. But even if it converged, it wouldn't matter. Like for example, if this second term came out to be 5, if I add 5 to something that, some other term that has no limit, it still diverges. So if you ever get that some part of it diverges, you're done. All right. This one here. So is there any value of x here that's going to make this, where this function is going to be undefined?
1.
1. So 1 is in my interval. So that means I need to split this up into 0, 1 for x minus 1 dx plus the integral from 3 to 1 of 1 over x minus 1 dx. And let's deal with the left-hand side of this first. So the limit as t approaches. So 1 is the x value where this becomes undefined. So my limit is going to be as t approaches 1, but from which side? The left or the right?
Left.
From the left. Yep. So this is what I have. And what is this antiderivative?
Natural log of x minus 1.
Natural log of absolute value of x minus 1. Evaluated from, oh, I forgot my limit operator. And that one, or not 1 minus 1. 0 minus 1. So now you're kind of seeing why the absolute values are important. Because usually the natural log of -1 is not defined. But since really what I want is the absolute value, this becomes natural log of 1, which is well defined. That goes to 0. So now I have this limit. The limit as t approaches -1 of, or 1 from the left, of natural log of the absolute value of t minus 1. What do we think about this limit? Is this well defined when t equals 1?
No.
Now let's think what happens as t gets closer and closer to 1. This is going to tend to the natural log of 0. Is the natural log of 0 well defined? Actually, let me say this a different way. This is going to be equal to the limit as t approaches 0 from the left of the natural log of t. What happens if you take the natural log of smaller and smaller positive numbers? So hopefully you remember the natural log graph looks something like this. As I get near the y-axis, then the natural log graph it gets arbitrarily negative. It'll just approach negative infinity without bound. So because of that, the integral from 0 to 1 of 1 over x minus 1 dx diverges. Because of that, what do we do now?
Means the second integral diverges.
So it doesn't necessarily mean that the second integral diverges. I mean, it probably does. But if the integral from 0 to 1 diverges, what does that mean about the integral from 0 to 3?
I guess I meant like since that part diverges, it means the entire diverges.
Yeah, so basically if I can't find the area on the interval 0, 1, I have no hope of finding the area on the interval 0, 3. So that one diverges. Yeah, let's go ahead and do this one. We'll go ahead and finish it up. So, are there any values on this interval where this this function is undefined?
Zero.
Zero. So I'm going to set my limit there, approaching from the right, of this integral from t to 1 of the natural log of x dx. So how do we handle this integral of natural log of x?
Integration by parts.
Yeah, so we'll use integration by parts. Since we have a good derivative for natural log of x, we'll use that. So then this one here becomes this limit as t goes to 0 from the right of x natural log of x minus x from 1 to t. One times the natural log of 1 minus 1 minus t times the natural log of so natural log of 1 goes to 0. So here's our limit as t approaches 0 from the right, -1 minus t natural log of t plus t. So -1 is what it is. This term in the middle is probably the one that needs the most attention, but obviously this last term will go to 0. And just really realizing where we are for time, I will tell you this limit right here of t natural log of t. So as t approaches 0, so this right here, this t will go to 0. This natural log of t will go to -infinity. But the rate of change of t is greater than the rate of change of the natural log of t. So basically this whole thing goes to 0, which means you get a convergent integral with a value of -1. Any questions there? Go ahead, Mona Lisa.
I was gonna say, is this section on the test too?
It is. So, yeah, and this is the section is too. I'm going to post the homework for it tonight, like right after I get off the line with you all. Just a reminder, I put some review material in on Canvas. If you look on modules, there's an exam one prep module on there. I would really advise you take a look at sooner rather than later. Other than that, I'll wish you all a good weekend. And if you need anything at all over the weekend, please email me or reach out on Slack or reach out to each other on Discord or whatever you're using. But yeah, there's quite a lot of stuff to review, and yeah, get started on it and let me know how I can support you.
Thank you so much, Professor.
Yeah, thank you.
Yeah.
Professor, I tried that stuff out of the CCAX. It's always like there's an odd term somewhere, like, you know.
Which one is this you're talking about?
The one, the integral of CCAX, like.
Yeah. So.
But I was sort of like trying to, I mean, like, I know there's like, we can do it in the integration by parts, but I just want to try out, like, see if there's any other way and like understand like why only certain ways work and like certain things don't work.
The tools you have. In fact, I don't even think integration by parts will work for this. I think we tried it. I will send you one way that I know how to find that integral, but it's pretty complicated. So, and I guess I should have mentioned this, but this is not an integral I'll be expecting you all to deal with for an exam.
No, but it's interesting. Like, I want to work.
Oh yeah, absolutely, yeah.
I'll try. Maybe I'll try it out.
Yeah, give it a shot.
Yeah, thank you.
Thank you, Rios.